Okay, so welcome back to another video. Here's a nice partial sum closed form that we want to solve for. So we have that r is equal to 0 for our beginning index all the way up to n being, of course, being the natural numbers, of r squared, and then multiply with n choose r, our little nice binomial coefficient. So with a binomial coefficient like this, how exactly would we want to find a closed form for this? Well, the only thing you really need to use is, of course, utilizing the binomial theorem, which is, of course, the expansion of, the binomial products, for example, for x squared or the power square or cube, etc., etc., and then it comes up with that using that form. So we actually just utilize that theorem with its formula for its formula, and then we actually try to utilize a little bit of algebra manipulation to it. Then easily we should be able to get what we need to do. So within this process, we're actually going to have to do a little bit of creating, well, not exactly creating, but utilizing several equations such that we have to perform some addition, or mainly addition. I almost said subtraction, but it's mainly addition, so that we combine the equations together to actually help utilize to achieve the closed form that we want from our given. So with that, why don't we actually just jump right in. So our nice little binomial theorem, specifically if I were to have in the form of 1 plus x to the power n, if we utilize that binomial theorem from there, so we know that the closed form has the nice formula of r equals 0 to n of our index of n choose r of x to the power r. Okay, so now, of course, let me label this as equation number 1. And then what we're going to do here is that we're actually going to differentiate both sides of this in respect to x. So by doing so, that means on the left-hand side, if we take the derivative, that means that's going to be n and then multiply with 1 plus x to the power n minus 1. And then differentiate the right-hand side, so of course that's going to be the infinite or the partial sum of r, and then n choose r, then multiply with x to the power r subtract 1. So let me label this as equation number 2 for both sides. And then next thing is, of course, we're going to actually differentiate this a second time for our beginning. So that means differentiating the equation above. So now we'll get that this is going to be n, then multiply by n minus 1, multiply by 1 plus x to the power n subtract 2, and then differentiating the right-hand side. So that means the partial sum r is equal to 0 to n of r times r minus 1 multiplied by n choose r, and then multiply by x to the power r minus 2. Okay, so with that being equation number 3 over here. So next, what I'm going to do here is, the next step is that let's actually substitute x equals 1 to equation number 2. So with that, let's switch to a different marker for this. So let me actually write this step down. We'll let x equals 1 into equation 2. Well, rather, I'll say substitute x equals 1 to 2. So with that being the case, then that means that this is actually just going to be simply n times 2 to the power n minus 1. And then set this equal to our partial sum of r is equal 0 to n of r, and then multiply by n choose r. Now the next thing I'll do is let's actually substitute x equals 1 to equation number 3. So what that will yield us is then that's just going to be n, and then n minus 1, and then multiply by 2 to the power n subtract 2. And then we're going to set this equal to, so do the same thing. So from n, r is equal to 0 to n of r, then r minus 1, and then n choose r. Okay, so let me actually then label these two things that we substitute as equations 4 and 5 over here. Then the next thing we're going to do is that we're then going to add equations 4 and 5 together. So then doing so, we're going to have n and then times 2 to the power n minus 1. Add this with n times n minus 1, and then times 2 to the power n minus 2. Then set this equal to, so we have our sums over here. So n, r is equal to 0 of r, and then n choose r, add this with our partial sum again. R is equal to 0, and then all the way up to n of r times r minus 1, and then times n choose r. Okay, and then just to do a little bit of some algebra over here on the right hand side, of course, you can exactly combine these terms together because they do share the same index. And then what you'll notice is that you can also factor out that we have a n choose r times n choose r. So if you actually put this back together, so that means this is actually just going to be factoring that out. So then this over here, in other words, this is the same thing written as n choose r, and then that's the same thing of all that being multiplied by 1 and then plus 1 minus r, which of course then is going to help reduce this down to just r squared and then n choose r. Okay, and so with this being the case, so now over here is that we can actually rewrite things a little bit different over here for the our left hand side. What we can do here is that I'm going to change this so the n minus 1 we want to get that's the same exponent as n minus 2. So to do that, we can actually do a multiply and divide a 2. So basically multiply and divide a 1, the same thing, but instead it's the 2. So by applying that, we're going to get something similar of this fashion. So 2 times n, and then times 2 to the power n, subtract 2, and then plus n times n minus 1, and then multiply by 2 to the power n, subtract 2. So really it's supposed to be equal. I kind of misaligned that a bit, but that's okay. Okay, so now if we actually do a little bit of some factoring out, we can actually factor out the n times 2 to the power n minus 2, and you'll notice that this is going to be, so doing so, n, and then, well first n and then times 2 to the power n minus 2, and then that will be just 2, and then add this with n subtract 1, which then becomes n times 2 to the power n minus 2, and then it becomes n plus 1, which basically just completes it because this is actually taking the sum of this, which is what we want to find the closed form of. So therefore, we just complete the proof, our closed form. So therefore, the product sum, r is equal to 0 to n of r squared and then n choose r, is simply just equal to n, then multiplied by n plus 1, and then multiplied by 2 to the power n minus 2. That actually completes all that up. And no matter what you choose for any natural number n, it's going to verify for all cases just like that. Simply, everything that we did is using in terms of just by starting off with just the simple binomial theorem with this little formula over here. If we plug in this case, whatever variable for y equals 1, and then put the expansion out, utilize some of its properties by, well, not exactly properties, but more of getting a little creative by actually applying a little bit of calculus involved and then getting something a little bit creative to where we actually do achieve what we need to achieve. So yeah, that's pretty cool if you ask me.